You ever watch a robot move and just wonder how it works? I mean, with that kind of incredible precision? It's so easy to just see it happen and not think twice. But how does an idea, just a command in software, turn into the exact electrical pulses that make a motor spin or an arm grip something? Well, today we're going to pull back the curtain on that whole process. We're going to trace the journey from a big idea all the way down to the raw voltage.
This, right here, is the central mystery we're tackling. How do you go from an abstract thought to a physical, real-world action? And let me tell you, the bridge between those two things isn't magic. Nope. It's a really fascinating mix of physics, some predictive math, and some seriously clever engineering that we're about to unpack.
And this image, it just captures the whole challenge perfectly, doesn't it? Up top, you see the plan. A nice, simple, elegant curve from point A to point B. But what the robot's controller actually has to figure out is what you see below. The exact position, the exact velocity, and the exact acceleration for every single millisecond in time. Turning that simple line into a perfectly timed dance of motion, that is the art and science of robotics control.
So to really get this, we need to look at the whole chain of command. Think of it like a hierarchy, right? A big, abstract idea at the top gets broken down into smaller and smaller, more concrete instructions until you're left with nothing but raw electricity. Everything kicks off at the very top with something called task planning. And this is the simplest instruction you can imagine, like drive to the end of the hallway. From there, the robot builds a little model of its world, plans out a sequence of actions, and then starts to execute them. But that's just the high-level strategy. We're going deeper, way down into the low-level tactics that make the movement itself actually happen.
Right, so while motion planning is this huge, complex field all on its own, robotics control, which is what we're talking about today, it lives at the very bottom of this pyramid. It's all about taking that planned path and figuring out the exact velocity needed to follow it, and then, right after that, you have actuator control, which takes that velocity command and turns it into a specific voltage sent to the motors, the actual muscles of the robot. This is where the digital brain meets the physical body.
So, how does a robot actually pull off that plan with any kind of precision, especially when, the real world is messy and unpredictable? Well, it all boils down to one single fundamental concept that separates a dumb machine from a smart one: the idea of feedback.
First, let's look at what not to do. This is an open-loop system, and a toaster is the perfect example. You give it a command, right? Toast for 3 minutes, and it just does it, period. It doesn't check if the toast is golden brown or turning to charcoal. There's no feedback. A robot running like this would be told to drive forward for 5 seconds, and it would just keep spinning its wheels even if it's slammed into a wall at second 2. Not great.
Now compare that to a closed-loop system. This is the smart way. You give it an input, like setting your thermostat to 72 degrees. The system then uses a sensor to measure what the temperature actually is. And here's the crucial step, this error calculation. It compares where it wants to be with where it actually is. If there's a difference, an error, the controller takes action, and it keeps taking action until that error is 0.
So yeah, feedback is everything. It's the secret sauce. This ability to constantly measure, compare, and correct is what lets a robot navigate a messy room, or adjust its grip on a delicate egg, or balance on 2 legs. It is the absolute core of all modern robotics. Okay, but before we can write the software to control a robot, we have to understand the physics that are working against us. See, every physical object has this natural tendency to bounce, to wobble, to oscillate. And our job, as control engineers, is to tame that wobble. We start with the simplest model you can possibly imagine, a mass on a spring. That little block, M, that's the mass of our robot's arm, let's say. And the spring, K, that represents its stiffness, or how flexible it is. Now, if you pull this block and let it go, in a perfect, frictionless world, it would just bounce back and forth forever. That oscillation, that's the natural behavior we need to get a handle on. And this brings us to a super important concept, natural frequency. You can think of this whole equation as a battle. The spring's stiffness, K, it wants to snap the mass back really fast. But the mass, M, has inertia, and it resists that change. The result of this tug-of-war is the frequency at which the system just loves to vibrate. And you have to be really careful not to accidentally push the system at this frequency, because that could cause wild, uncontrollable shaking.
But of course, in the real world, things don't bounce forever. Friction always wins. So to make our model more realistic, we add a damper, labeled C. This is just like the shock absorber in your car. Its whole job is to resist motion. The faster you try to move it, the harder it pushes back. And this complete system, mass, spring, and damper, is pretty much the standard model for a robot's physical dynamics.
So from this complete, realistic model, we can calculate one single, almost magical number that tells us everything we need to know about how the system is going to behave. It's called the damping ratio, or zeta. And this one little value predicts the exact character of the robot's movement. It's like a crystal ball for motion.
Okay, let's look at the 4 things this ratio can predict. That blue line? That's an undamped system, a ratio of 0. It just oscillates forever, a perfect bounce. The green line is underdamped. It gets a little too excited, overshoots the target, bounces a bit, and then finally settles down. The orange line is overdamped. It's sluggish and slow, kind of like a heavy door closer. But that red line, that is critically damped, the Goldilocks zone. It reaches the target as fast as physically possible without any overshoot at all. And for a robot, that's usually exactly what you want.
All right, so now we understand the physics that a robot is fighting against. Let's look at the software we use to win that fight. For over 100 years, the undisputed champion, the workhorse of control theory, has been this elegant and powerful algorithm called the PID controller.
At its heart, a PID controller is just a closed-loop system. It takes the set point, that's where you want to go, and it subtracts the measured process variable, that's where you actually are, and that difference creates an error signal. The controller then takes that error and processes it in 3 separate parallel ways: proportional, integral, and derivative, to cook up one single control signal to send to the motors. Let's break those 3 down, starting with P for proportional. This is the most intuitive part of the whole thing. Let's use a car analogy. If the stop sign is way far away, your error is big, so you push the gas pedal hard. As you get closer, the error gets smaller, so you naturally ease off the gas. It's simple, but a controller that only uses proportional action will almost always overshoot and then oscillate around the target. It's a bit too aggressive on its own. And that's where D for derivative comes in. This is the brakes. The D term doesn't care at all how far you are from the stop sign. It only cares about your speed, the rate of change of your error. If it senses you're closing in on the target too quickly, it applies a braking force to keep you from flying right past it. This is how we kill those oscillations we were talking about. And finally, we've got I for integral. The I is the perfectionist of the group. Imagine you've stopped your car, but you're maybe 2 inches short of the line. The P and D terms might be 0 because you're not moving and you're super close. But the I term sees that tiny, persistent error, and it slowly builds up force over time. It integrates the error until it's just enough to give the car that final, gentle nudge to hit the target perfectly. So in the real world, engineers have to tune these 3 terms, and it's basically a 3-step recipe. First, you crank up the proportional gain, the P, to get a fast, snappy response. Then you add in the derivative gain, the D, which acts like a brake to get rid of all that overshoot. And finally, if you need it, you add just a little bit of integral gain, the I, to clean up any tiny final error and really stick the landing.
Now, PID is a powerful classic. It's legendary. But modern robotics problems, we're talking autonomous cars or dynamic walking robots, they demand even more advanced strategies. So let's take a quick peek at what's on the horizon.
On the left, you've got Model Predictive Control, or MPC. Now, instead of just reacting to the current error like a PID does, MPC uses a physics model to predict the future. It's like a chess master planning a whole sequence of moves to find the absolute best path, all while respecting rules like speed limits. Then on the right, we have reinforcement learning. And here, instead of writing out a bunch of equations, we just let the robot learn how to control itself inside a simulation, rewarding it for good moves and penalizing it for bad ones. It basically teaches itself.
Which leaves us with a final thought. The PID controller is a brilliant, timeless piece of engineering that's over 100 years old. But as AI and reinforcement learning get more and more powerful, are we approaching a future where robots don't need to rely on human-written equations anymore? A future where they can learn and invent entirely new ways to control their own bodies? The answer to that question is going to define the next generation of robotics.